Okay, so we are starting from the beginning. I'm going to just transition so we can so you can also see the slide with me. All right. So biomolecules. I'm going to try my best to take this as easy as I can. Now, one of the things you should know, if at all, by now from previous studies, is that uh, organic compounds, there's a branch of organic of chemistry known as organic chemistry, where we study organic molecules or organic compounds. Right? Where I'm going to is this. One characteristics of organic compounds is the fact that sorry, excuse me, is the fact that they all contain carbon. They all contain carbon. Now, apart from carbon, they contain carbon and hydrogen. In fact, most of them also contain nitrogen. Right? Most of them also contain nitrogen and oxygen. So, for example, carbohydrates, proteins, lipids, urea, all those guys are examples of organic compounds. So, from the beginning of this slide, you see that they said biomolecules are composed of elements, four elements, which are C, H, N, and O. What I want to quickly let you know here is this, because now we're looking at biochemistry, focus majorly on these people studying medical courses, nursing, MLS, those guys. So what I want to let you know is this: everything that makes up your body, everything that makes up your body consists of only these four elements: the carbon, hydrogen, nitrogen, and oxygen. Every single thing, right? Though when you look at the cells, they will say it is majorly aqueous, but that's not where I'm going. Even that aqueous is water. I say hydrogen and oxygen. If you look at every other thing, the proteins, carbohydrates, lipids in your body, they are all organic compounds. They only consist of carbon, hydrogen, nitrogen, oxygen. Everything, including the way you think, is still the same four elements. All right. So skipping all these boring stories we have here, because these ones are boring stories. There are things you can easily know. But please still ready to. I will still try and set questions maybe after the class under this story that is here. So, but for now, let's not be our focus. Let's not waste our time. Let me go a bit further. Now, biomolecules in living things. Now, biomolecules can be divided into two. That's what the next part of the story will try to do. Will try to tell you. So let me quickly just break it down. Biomolecules can be divided into two. We have the small ones. We have the big ones. Now, the small one is the what we call micro, small, micro, big, macro, MACRO. So whenever the biomolecule is small, we call it micro biomolecule. If it's a big one, we call it macro biomolecule. It's as simple and short as that. So now again, the small ones are used to make the big ones. I've done a short video on this before. Those that have not posted it online, which I will do that at least between now and the end of the month. So the small ones, are the microbiomolecules, are used to make the big ones, macrobiomolecules. You can think of it as, in fact, you don't even think of it, monomers and polymers, so to speak. So if you look at some examples of the microbiomolecules, we have amino acids, we have simple sugars, or what we call monosaccharides. Then we also have what is it, nucleotides. These are examples of micro biomolecules, and they are used to form the macro. For example, amino acids, which are examples of the micro biomolecules, are used to form the big one, which is what, protein. If you consider what is it called, nucleotides, which is another micro biomolecule, it is used to also form the big one, which is nucleic acid, RNA, and DNA. If you look at simple sugars, monosaccharides, they are used to form complex carbohydrates like starch, glycogen, chondroitin sulfate, as chondroitin 4 sulfate, chitin, or what you call chitin, how do you pronounce it, and different other complex polysaccharides, carbohydrates. So this is just basically how it works. Let me skip again. Now, Some important attributes of biomolecules which may be used in study of biophysical techniques. Now we're talking about physical attributes first. The mass, the volume, the density, the charge, the shape, energy. For now, you don't need this. I will explain it when I feel it's important. So let's go further first. Now look at this now. Macro, this is the big one. Remember, the big one, macro. So macro usually refers to four major classes: proteins, nucleic acids, right? Where are they again? Lipids, good, and polysaccharides. Okay. Now, what I want to say here, what I want to lay emphasis on is the fact that lipids are not true polymers. Though they are examples of macro because they are kind of big, but they are not polymers. Why? Because it's not like you are going to find, for example, in amino acid, you have amino acid being a micro molecule. It's not like the way you form proteins, you have amino acids, forming polymers, joining to form polymers before you can get proteins. Right? You can have glucose, so many glucose joining themselves to have, starch or glycogen. But in lipids, it's different. You cannot have a small lipid joining to form a big lipid. No. The only thing is just that you can get fatty acid, which are smaller types of lipids. These guys, when you have fatty acid joining glycerol, you can now get a more complex lipid like the triglyceride. Yes, but it's not like you call them polymers. They're not really polymers. That's what they're trying to say, that they are not technically always true polymers. But they can form large hydrophobic assemblies of the smaller lipids like fatty acids, glycerol, and the rest of them. So that's where I want to emphasize a bit. So let's go on. Simple biomolecules. I know I'm kind of taking it fast. You can always ask me a question, but trust me, you will still understand it. And when you start asking questions, you will see that you are getting it. Now, simple biomolecules. I'm talking of, obviously, simple is still a micro biomolecule. You mean the smaller ones. Now, first we are taking amino acids. Later we can take other ones. Amino acids are organic molecules found in living systems. We all know this. But what we want to talk about here is the fact that amino acids are used to form proteins. When you keep on adding polymers of amino acids, what you see is that you will get what? You will get a protein. Right? That's where we are going to. I'm also trying to see whether I can, make a drawing here. But unfortunately, I'm not really seeing where I can make a drawing. Maybe I should open paint. Bear with me a bit. Bear with me a bit while I try to show you a drawing. I didn't prepare. I would have been able to use the board behind me, but okay, I think I have a marker, but let me see whether I can use paint to do something. If I cannot use paint to do something, then I'll get a marker. Okay, I think I can use paint to do something. So I'm just going to share my screen. So I'm just going to share the screen. Please bear with me a little bit. Okay, I'm struggling a bit to share paint with us. I'm not sure why. Well, okay, I'm sorry about that. Paint is not showing. So let's look at how to use the board. If you can see what I'm writing, please comment on the comment section so I can know if I'm to proceed or I shouldn't proceed. Can you see what I just wrote? on the board. Is there somebody comment so I can know if you are following me? Any comments? Any comments? You can't see it. Okay, I'm sorry about that. Okay, well, let's just use the slide like that. I'm sure we can still follow. All right, so if you consider the slide I have currently on, you would just notice only these spots for now. These spots where we have carbon chain. All right, so you would see that there is one carbon atom in the middle. This carbon atom here. Now, what I'm trying to let you know is this: in all amino acids, all 20, and because for now you will learn about 20 amino acids. Okay, so for now you know that you have 20 amino acids, though there are more than that, but for this level you only care about 20. Now if you consider this carbon atom in the middle, that's what I'm going to, you would see that there is an hydrogen atom close to it here. We also have a carboxylic acid functional group here, that's COO minus. If it was not, this is in ionic form. It's just in ionic form, you would have seen COOH. Then you also have an amine group here, NH3 plus, also in ionic state. If it was not in ionic state, you would have seen NH2. It means that this nitrogen have accepted extra one hydrogen that it can collect. Hence, they need to put the small plus on it, that small plus above it. Alright. The same thing, this COOH is in ionic form, so it has lost an hydrogen, which is why you have that small minus just above it there. You see this one. So when this COOH loses its hydrogen, this N here can actually accept that hydrogen, becoming 3, and then you now see the small plus written above it. But where am I going to? Where I'm going to is carbon. We always have 3 in amino acid. Now every amino acid will always have a carbon, this middle carbon here, that carries 3 different things. It must carry an hydrogen molecule here, it must carry a carboxylic acid functional group, and it must also carry an amine group, NH2, or in ionic form, NH3. So it is only the lower portion where you have R, it's only this lower part that changes, and we call it the side chain or R group. The R group. So for every 20 amino acid, what differentiates them is just the R group. Every other thing remains the same. I don't know if you are following me. So if you look at it here, it's written R, a variable side chain. So it's a side chain, it can change. That is the main thing that distinguishes amino acid A from amino acid B. So for example, in the 20 we have, there is only one amino acid that is achiral. Achiral. I'm going to also open okay, since I can't work with paint, I should be able to work with my second screen here. Okay, where we have questions. So it's on MS Word, so I should be able to write some things on it, which is a good thing now. So please follow me. Let me kind of shorten this thing so you can see the full screen. I'm going to open it now. So let me transition. Okay, this is where I saved some questions. But for now, I don't need the questions. We are coming back to it. What I want to do is I want to, write something. Achiral, different from chiral. The question becomes, what is chiral and what is achiral? When we look at the word chiral, it means that central carbon atom I told you about, carries 4 constituents, right? So by the side, it can carry, let's say, a compound A. By the left, it can carry, let's say, a compound B. just below it, let me insert a text box, a small text box there. Sorry, just want to insert a little text box that I can use to explain this concept. Okay, so let's say just above it, it has another letter C. That's another letter, or E. Let's use E. Okay. Bear with me. Okay. Now and again, just below it, the way we have E above, we can also have another compound, let's say D. And I'm trying to recreate an organic chemistry something, the way we do the way we draw carbon. Just trying to, for subsequent times, I will look for how to get, a writing, something I can use to write and we can all see clearly. For now, just bear with me. I'll make this session short. Maybe tomorrow we can do another session, or even later in the evening if there's time. You can do, although still with your own permission. So consider this structure I have here. Coming, bear with me a bit. Let me bring it down. Yes. So consider this structure I have here. Imagine, this is normal carbon, the way you normally carry hydrogen, oxygen, different things, the way it used to be. But if all the substituents the carbon carries are all different, you say that that particular carbon is chiral. It is chiral. But if maybe one or two of them are the same, for example, if this B here is an A, now you now have two of the same constituent on carbon. Excuse me. So we have A here, we also have A here. Or maybe we can have E above, like we have here, and we can also have E above. So far you already have a substituent appearing more than once. It is now termed achiral. So what am I trying to say? There is only one molecule, there's only one amino acid rather, that is actually achiral. So let's assume this is an amino acid here. Alright, let me try to make one amino acid. Good. Bear with me. Just trying to use my, let me not use 3, let me use 2. Remember I told you it will be 3 when it has accepted another extra hydrogen. Please don't forget. The same thing, you have a minus up here if it has lost an hydrogen. If it has not lost, it will still be COOH. So this is how it used to be. While up here, you will still have an hydrogen. You will still have an hydrogen group up there. What am I trying to say? Every amino acid has this NH2, it has this COH, it has this H. It's only this last one down here that I called the R group. Sorry, it's only this one down here, trying to edit it, I call the R group, right? And this R group being the side chain, which I told you can change. So if we consider an amino acid known as glycine, glycine here is the only achiral amino acid. Why? Because its own side chain is H. That's its own side chain. That is why you now have H up here, you now have H down here. That's why we can call this one an achiral amino acid. It is the only amino acid that is achiral. Every other one, for example, when you go to the next amino acid, you have alanine. Alanine, the side chain down here, the R group is CH3. CH3, just like what you have, what I have just written. So CH3, just like this. When you have this amino acid, this is alanine. But you can see that it is no longer achiral. It is now chiral. Why? Because H here is different from NH2, it's different from COH, it's different from CH3. All the constituents are what? Different. That's why we call them chiral. The same thing, every other amino acid, they are all chiral. So basically that's what I want to buttress for now. Let me go back to the slide for now. All right, okay. So now also attached to the central carbon. Now we said that the central carbon has a carboxylic acid group attached to it, and a what now? And a okay, yes, has a primary amine functional group. That's where I'm going. That amine group now, or amine group, how do you pronounce it? Is the NH3 that you see here, or NH2 if it has not accepted another hydrogen. So that is the amine group. It also has carboxylic group attached to essential carbon. Then also attached to essential carbon is a variable side chain, which is the R that I told you about, that can change depending on the amino acid, right? So side chain differentiates most amino acid. 19 of the 20 have central carbon to be chiral. That I also have to explain now. The amino acid is said to be chiral if it has two of the same, which is only one of them that is achiral. The remaining 19 are what? Chiral. That's what this slide is saying now. So you see that what I'm explaining, you can just go through the slide and understand them. Now the next a little bit difficult thing to understand on this particular page of the slide is the issue of L and D, which is not really also a problem. Now what I was trying to say here is this. When we are in organic chemistry, in chemistry, when you're studying organic chemistry, you learn that there's something as isomerism. A type of isomerism is called stereoisomers. The type of isomerism known as stereoisomers that can create L and D. The other type of isomerism, some can create EZ configuration, E and Z. Some can get R and S, just like that. But for now, we're concerned about L and D. It has a full name, but it may not be your business. Let me clear this for now. Right. So let me delete this part. Sorry. And I want to kind of bring this thing down so it will not affect every other thing I will be typing. Okay. So there we go. Yeah. Now I said L and D. What do I mean? L means level rotatory. That's what it just means. Why D here? D means dextro rotatory. What does that mean? Now, most organic compounds like sugars, carbohydrates, and amino acids, they are able to rotate plane polarized light. This grammar for now may not really be your business, so I was trying to write something. Let me bring back what I was writing. You can see it. Sorry, I forgot to transition on time. So look how we have here level rotatory, dextro rotatory. All right. What I'm trying to say is that these compounds can rotate plane polarized light. If it rotates plane polarized light level, which is L, but if it the back and to the right rather, it is D, and that's what you see here when they say L and D isomers. Right. Now these two isomers are non-superimposable. What does that mean? If you look at the mirror, you would see yourself in the mirror, just like the way I'm seeing myself now, even on this video I'm making. Now, surprisingly, I don't know how it is shown on your screen, but surprisingly, the hand I have up here is my left hand. The one I have up here is my right hand. But let's look at just my hand. Forget about the mirror image now. If you look at just my hand, even when they look the same, they look like mirror image and they look the same, but I can never superimpose them. I can't, because you see that it's not really making sense. It's like going opposite way. There's no way I will fix it that will make it look both of them face forward while simultaneously being, you get, think of duplicating my palm and putting one in front of the other. There's no way you do it that will look like that. Now remember, even when they are the same, They are mirror images of themselves, but you cannot really superimpose them. That's what it means. So going on, but again, they are mirror images. So whenever you see that it rotates plane lines to the left, it is L. It will be to the right, is D. But that's BB grammar. You can't see the what do you call it, the polar what is the machine they use to calculate this thing? Forgotten the name. You can't see it for now, but we shall know how to draw the structure. Since we can draw the structure, consider, let me go back to the other one so you can see my slide. You can see what I'm projecting. So consider this structure I drew here for us earlier. Let me go down. Now sometimes you find people putting this COOH up, while the H will be here. Say for example, you see the COOH here, right? Whichever which way you see it, it doesn't matter. But you always notice one thing: the NH2 is always at the back. That's what you always notice, no matter the way they are drawing it, the NH2 is always at the back. You know why? Because it's the NH2 that actually tells you if that amino acid is L or D. Now, if it's by the left, the way it is here on my slide, it is L. So this is an L amino acid. Remember I told you that if you have CH3 down here, what you have drawn is alanine. So you can simply write, sorry, L alanine. So what you have up here now is L alanine. Remember I also said it's the same thing. Even if you replace this one back to COH and take here back to H. You know why? Because it doesn't matter. What matters is the NH2 that matters. So when you find that the NH2 is by the left, what you have there is L alanine. But if you find that the NH2 for some reasons is now here, if it's in front, by the way, if it is in front, we call it sorry, bear with me. We call it NH2 rather. So we just like to put the H in front of N when it's at the back, because it will look as if the bond is going to be on H. So that's why we don't do that. We at the back we alter it so that it look like the bond is on N, because the bond is actually supposed to be on N, not on C. Alright, so if we have gotten that, we can go forward. Okay, so let's say for any reason here we have COOH. So similar thing, we can't put the H close to the bond, so we just say HOOC, so that you can understand that the bond must always be on C. So if for any reason you find the structure like this, right? For any reason you find a structure like this, what you okay, sorry. So I'll transition now. So if for any reason you find okay. So now let me replace the NH2 back to where it was, so that I can go back to L sugar, L amino acid rather. Okay, just like this, yeah. So what we have here, as I was saying, is an L sugar. Please bear with me. I'm trying to. I'm just trying to increase this one. Okay, yeah, I'm there. All right, so back to where we are saying. Now imagine we have this and its mirror image here that will give us D. You know they are also going to be non-superimposable. That's what that slide was trying to tell us about. So remember, what the only thing you should know here is that whenever the NH2 is by the left, that's the way it is now, it is what? It is it's going to be called L amino acid. But if for any reason it is by the right here, the NH2 is by the right, is going to be called D amino acid. Now what you should note here is that in nature, almost all amino acid, almost all of them in nature exists in the D conformation, in the L rather, in the L conformation. So when you see amino acid naturally occurring in the body, it's mostly going to be in the L state. So you see L-alanine, L-glycine. Let's go on to it. Let's go on to it and be fast. Now, amino acid can be grouped based on the chemical structure of their side chain. Remember we said that those side chains can differ, that there are different side chains, and that's what differentiates glycine from alanine, from valine, from leucine. If I scroll down to the end of this slide, you will see the amino acids, 20 of them. You see glycine, alanine, valine, leucine, isoleucine, and so on and so forth. It is the side chain that differentiates all these guys. Like I tried to explain, that all amino acids must have those three things at the top of it. Let me go back to my other structure. Now this structure, I was trying to explain that all amino acids are all going to have the H, the D's, the D's. So it's only this R group that is just going to change. So let me go back to the amino acids we have. So please follow me. What am I trying to say? Based on what the side chain are, you can see them, different side chain. Look at the way valine is. Alanine is CH3, glycine is H. Leucine looks like this. If I go down, you see that some of them has organic structures like benzene, aromatic compounds. These are aromatic compounds. You see benzene ring, you see phenol ring. This is what we call an imidazole ring, what we have in tryptophan. Imidazole, what we have in tryptophan. So they're different like that, depending on the kind of R group. Differentiate them. Some of them, just like these ones, let me go back there, just like methionine, some of them contains S, sulfur. Look at this one too, sulfur. So these two are called sulfur containing amino acids, both of them collectively. There are some of them that have OH, like this guy. They are called hydroxyl group containing amino acid. We have tyrosine, we have threonine and serine. You will find them now. Yes, I found them. Serine and threonine. You get what I mean? So what I'm trying to say is that depending on what is on the side chain, we can classify them. You can see histidine has something funny, known as an amino group. That's not what we are going for now. Rather, an imidazole group. Imidazole group that histidine has. The one that has amino group is proline. This is it, proline. So depending on what it has, now some of them, this is where I'm going to, some of them have another NH2. Similar to what we have up here. It makes this guy basic, because when you have more of this positive charge, it's most likely tending to an alkaline. But if you have extra of this negative charge up here, this COO minus is making it acidic. So you see that there are some of them that have extra COO minus. You see that even from the name, you can tell there's an acid, glutamic acid, because it has COOs like this one too, COO minus, aspartic acid. So where am I going? Depending on what you see down there, you can classify it, and that will be your assignment. So go and know them based on classification. I've given you some of them already, because you look at it now. Aliphatic chain, based on aliphatic chain, right? You will see that there are examples of them. Aliphatic just means they have hydrocarbon chain. For example, CH2, 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 CH3. Let me just quickly see whether I can draw one organic structure here. Then I will project it for you. Let me go back to the other screen. Okay, so let's say I have so I'm trying to say that I can draw one organic structure for you. So for example, you can have CH2, no, the last one will be CH3. This one can be CH2, and have another CH2, CH2, and the last one again will be CH3. So where am I going? This is an hydrocarbon chain. It is looking like an alkane. So by the time you count, you see that how many carbons? 1, 2, 3, 4, 5. So this is a pentane. What you normally draw gradually by drawing, the lines above them. But this is what we have here as pentane. So whenever you see that the amino acid, the R group, is looking exactly like what you see in hydrocarbons, when you do the hydrocarbons, then you know that it's aliphatic in nature. So that one will be classified under aliphatic chain. Let's look at some examples. We have glycine. Glycine obviously only H. Alanine, CH3, looks like that. Valine, leucine, and isoleucine. Let's go check their structure so you can see. So you see, valine looks like hydrocarbon to me. This one too looks like hydrocarbon to me. Even this one too also looks like hydrocarbon to me. That's what I'm trying to explain, that if it looks like hydrocarbon side chain, they are all aliphatic in nature. So when you go up again, you see on that one, hydroxyl group containing, I showed you them, the ones that have OH, that's hydroxyl group, which are what? Thyroxine, the one that have a phenol ring. Phenol is benzene that has OH on it. So this is a phenol ring. Benzene ring that also have OH on it is phenol. So tyrosine contains hydroxyl group. You have serine, you can see the hydroxyl group here. You also have threonine, you can see the hydroxyl group here. Alright, so going back, what else do we have? So please know the examples of this classification. When you are talking about hydroxyl group containing, what are the amino acids that contain hydroxyl group? When you talk about the ones that are grouped based on aliphatic side chain, what are the amino acids that are grouped under there? Now again, some of them contain sulfur. Sulfur containing, there are only two, methionine. When we met in class at that time, I spoke about cysteine forming disulfide bond. It can't form disulfide if it does not contain sulfur on its structure. So let's go down and look at them. Yes, look at cysteine. That's the thiol groups. SH is called thiol in organic chemistry or in chemistry. So it is this S that it always uses to form disulfide bond with another cysteine molecule. But if you look at the other one, methionine, you also have SCS separate. This one does not form disulfide bond because S can only carry two bonds. It has one here, it has one here. And as you can see, the second bond is already occupied with CH3. So it is always hard to displace this CH3 group here. That's why methionine does not form disulfide. But if you look at this cysteine, it has one bond here. The second bond is just an H hydrogen atom. You can see that it is easier to displace hydrogen and form a disulfide bond with something else. You get? That's why cysteine forms disulfide bond. H is always so easy to displace. So what else do we have? Then we have acidic and basic. Like the ones that are acidic are the ones I told you that contains extra COOH or COO minus, like the way this COH that we have here, like the way you have in glutamic acid and aspartic acid. Where are they? Yes, so you find them. I saw them. Okay, yeah, glutamic acid. So you can see the second extra COO minus it has. Aspartic acid too, having the same. When you enter basic, basic mostly used to have extra NH2, like asparagine, like glutamine. What else? Like histidine, you can see it has several other NH. So it's also basic in nature. Arginine, you can see. Lysine, you can see. They are all basic in nature, right? So you'll find them classified under the basic. You see them histidine, lysine, arginine, glutamine, asparagine. But then, oh, I skipped one, the aromatic ring. This one are very obvious. When we talk about aromatic ring, we're talking about the ones that have benzene on it. Benzene is the main reference aromatic compound in organic chemistry. So thyroxine, phenylalanine, tryptophan, they all have benzene ring in their structure. Let's go look at them. Phenylalanine does have a single benzene ring. The way you see it here, you can see the ring, benzene ring. Tyrosine has a phenol ring. Phenol, like I said before, is simply benzene plus hydroxyl group. That's called a phenol in organic chemistry. If you look at tryptophan, tryptophan has two in one ring. But if you look here, you see that it also has benzene. That's benzene ring combined with this pyrrole ring. Is this pyrrole or imidazole ring again? So you can see this organic group. So, but for the fact that it has that benzene on it, we already classify it as what? Aromatic amino acids. So know how to classify them based on their side chain. What is the chemical nature of that side chain? The chemical nature. From there, you can classify them into all these things we have here. Then finally, imino containing, which I told you before, proline is the only one that has imino group. For now, just know it. You don't need the chemistry of it to understand what type of structure a compound is or imidazole compound or the rest. I know your business for now. So structures of amino acid. they are giving there. So please look at them. Look at them. They said glycine is the simplest of them all, right? Having no stereoisomerism because it is not chiral. It is not chiral, it is achiral, right? So that's that for that. We have talked about this already, so you can look at the structures. Talked about the sulfur containing one that has thiol that can form disulfide bond 16. You get so which also helps in protein folding. We did protein folding earlier this week, so you can release to it. So just like that, shall different structure. Just know the structures. What you just have to. That's basically what you have to know. Now the final thing I will talk about. Now look at all these amino acids. It's the fact that amino acid, as we round up, can be abbreviated. You must not write always be writing glycine or alanine or valine. You can shorten them to gly, ala, val. We call them the three-letter code. Three-letter code. It's not always that simple, by the way. Sometimes it changes, but the worst of them all is a single letter code. Because, for example, glycine starts from G, so the single letter code is G. It all looks fine and sweet. Alanine starts from A, so single letter code is A. It looks fine and good. But what if you now go to glutamic acid? Glutamic acid starts with a G, is it not? But what single letter, look at it now, start with a G. But what single letter code should I give it? What single letter code should I give it? That becomes a problem. So for now, you may just have to memorize it because in your exam, you might be asked, or your tests, even whichever, you might be asked about single letter code. They might describe an amino acid for you with the single letter code. They may tell you an amino acid with single letter code. Why? Why? As what is the nature of the side chain? Option A, is it a sulfur containing amino acid? Is it an aromatic amino acid? Option B. Option C, is it aliphatic amino acid? Does it contain aliphatic side chain? Option D, does it contain hydroxyl group? Or let me know, is that one. Let's say, does it contain imino group? If you don't know what Y stands for, you will not know the answer. Look at it, say tyrosine. Remember that tyrosine is one that has a phenol ring, which is benzene plus OH. Then you can tell that okay, tyrosine is what? Aromatic. I don't know if you understand me. So you might need to also know the single letter code. That's the last thing I have to talk about. So for now, I can't help you here because some of those ones that already exist, like G, and you have glutamic acid somewhere down. Those ones they were formed from the Latin names. So I can't help you there. You have to just know it. There are 20 of them. Thankfully, only about 8 of the 20, I think 8 or 9 has that issue. But for the 3-letter code, it's so simple. You cannot think of gly, ala. There are still some exceptions though. For example, if you look at tryptophan, we didn't want to use tri again, so we just say okay, TRP. Again, if you go to glutamine, now glutamic acid is already glutamic acid. So what will be glutamine? GLN, the N you get asparagine, so N, ASN instead of using, and now you can't use ASP again because there's already ASP for aspartic acid, so you can't use. So now what do you use? ASN, just like that. So we also have okay, basically those are the ones that have issues when it comes to 3-letter codes, but you can see that they are easier to remember as compared to the 1-letter code. So know them and know them for yourself because you should know them. Glutamic acid being E, lysine being K, and so on and so forth, because there's already something that contains L before, so they don't want you to use the same thing twice. That becomes the problem there. So basically that's it for this class. I really hope you have learned. I'll be stopping here for now for today or for this morning in case you later can have another class today, which I doubt, but I'll stopping here for today until you see next time. But before I go, I don't know, can you send, if you have questions, type on the comment section. Let me just give 2 minutes for that, 2 to 3 minutes for that. Between now and the next 3 minutes, if you have questions, type it in the comment section. Let me see if I can answer live before I answer offline, because you can always reach out to me on WhatsApp, on email, whatever. You can always reach out to me. So but for now, before I go offline, before I end this live stream, do you have any question for me? Any question? So type it on the comment section. while I wait for you.